So, again, trying to make this seem like a reasonable type of thing. Now, the problem is that this isn't how we're going to use it. This is exactly backwards of how we're going to use it. Because we started with a point charge. And then I said I knew the field from the point charge so that I could calculate the flux through the surface to show that I got Gauss's law. Okay. Usually goes the other way around. So usually the way this will play out is that we're going to use Gauss's law to determine the magnitude of the electric field. So you want to pick a surface so that the E is constant over the entire surface. And so you can pull it out of the integral. And then what you get is an integral of a dA, which is the A, always. So it's a non-integral integral. Okay? And if it isn't, you're doing it wrong. If you can't pull that E out, we're not doing it right. Or it's not meant to be done this way or something like that. This is the only way it's going to play out for us. E will be constant over the surface. We'll pull it out and get the integral dA. That'll be the area of whatever surface or shape we happen to have. And then we can say that's equal to our Q over epsilon naught and then solve for E magnitude. You're like, but the Q is an absolute value. I'm like, yeah, but that's because if the Q is positive, you get a positive flux. Q is negative flux, and the signs cancel out anyways, and so we're all good. So it won't matter. Okay. So the way we do this is exactly the other way around. Okay. It's exactly backwards. Okay, so the way that we go is we say, well, we have some charge. Okay, and then what we'll do is we'll go and say that since it's a point charge, then what it will have is it will have what they call spherical symmetry. So if you rotate the page or turn the problem in any way, it looks the same. So a point charge has spherical symmetry. And so therefore that indicates that the Gaussian surface we will use is a sphere. Okay. Okay. And then we know that our electric field vectors are going to, point outward, like so. And then when we come in and we look at some little dA patch, that my electric field vector at that point and the area vector at that point are going to point in the same direction. So therefore our angle will be 0. Okay? And so the way this will go is that when we go in and we find our net electric flux over the Gaussian surface of E dot dA, we're going to argue that by symmetry, the electric field is constant over the entire surface. And since it's constant, you can pull it out of the integral. Again, if it isn't, we're doing it wrong. This is the only way it's going to play out. And so we will always end up with E dot the integral dA, which is going to be our E dot A, which At this stage, what we can do is we can write that this is going to be the magnitude of E times the magnitude of A times the cosine of the angle between them. For a positive charge enclosed, we expect outward pointing electric field vectors. We have outward pointing area vectors, so the angle should be 0. Again, assuming we have the symmetries matched up, and you need that. I mean, if you have a point charge, we can't be using cubes. That's a no-go. We can't integrate that. Okay, and so then cosine of 0 will just be our 1. This implies that what we had was some sort of positive charge, so this is our net enclosed charge over epsilon naught. And then what we'll do is we'll go in and say that my A was our sphere in this instance, so we get E times our 4 pi r squared is equal to the Q over epsilon naught, and then we divide and solve for E. That's K. This is effectively what they usually call Coulomb's law. Even though Coulomb's law is actually for the force between the charges, when we calculate the field due to point charges, we got this, and so this is often what they'll reference as Coulomb's law, even though Coulomb's law really was for the force, not for the field. And so what you can get is that from Gauss's law, we can derive Coulomb's law. So they are equivalent in that aspect.